Have you ever wondered how multiple devices share a common communication line without causing a short circuit in digital systems? Welcome to the intriguing world of digital logic and design, where the tri-state buffer plays a pivotal role. This unique logic gate has not two but three states: a logic high, a logic low, and a high impedance state. It's this third state, the high impedance or Z state, that allows multiple tri-state outputs to connect to a common bus without causing a short circuit. And this is why tri-state buffers are commonly found in bus systems, memory devices, and any scenario where multiple devices need to share a common communication line. So, you see, tri-state buffers are absolutely key to efficient and controlled sharing of communication lines in digital systems. Stay tuned as we delve deeper into the structure, behavior, and applications of tri-state buffers in the following scenes. So, what does a tri-state buffer look like? Well, it's a simple yet powerful component in digital logic and design. A typical tri-state buffer has three parts: a data input, a control input commonly known as the enable, and an output. Let's start with the data input. This is where the buffer receives the digital signal it needs to process. The signal can be either a logical high, represented by 1, or a logical low, represented by 0. Next, we have the control input, or the enable. This control input is the switch of the buffer. When the enable is set to 1, the buffer is active and the data input is passed directly to the output. However, when the enable is set to 0, the buffer turns off and the output goes into a high impedance state, often represented by Z or described as floating. This high impedance state is what allows multiple tri-state buffers to connect to a common bus without causing a short circuit. Finally, the output of the tri-state buffer is where the processed data signal is sent out. Depending on the state of the enable input, the output will either mirror the data input or go into a high impedance state. The symbol representation of a tri-state buffer is quite straightforward. Picture a rectangle. The data input and the enable input are two lines entering the rectangle on one side. The output is a single line exiting the rectangle on the opposite side. In summary, the structure of a tri-state buffer is designed to manage digital signals effectively. It receives a signal through the data input, processes it based on the state of the enable input, and then sends the processed signal out through the output. This structure allows for efficient data management, especially in systems where multiple devices need to share a common communication line. Therefore, the enable input controls whether the buffer is in an active state or a high impedance state. This control is key to the versatility and utility of tri-state buffers in digital logic and design. Now, how does a tri-state buffer behave? Well, let's demystify it with the help of a truth table. A truth table provides a concise way of illustrating all possible combinations of inputs and their corresponding outputs in a logic circuit. Imagine a tri-state buffer with one data input, one control input, which we'll call enable, and one output. The function of this buffer is determined by the state of the enable input. When enable is set to 0, no matter what the data input is, the output will always be Z, representing a high impedance state. This is akin to the buffer saying, "I'm not participating right now, someone else can take the lead." On the other hand, when enable is set to 1, the buffer is in an active state. This means it's ready to transmit data. Now the data input comes into play. If data is 0, the output will also be 0. If data is 1, you guessed it, the output will be 1. So when the buffer is enabled, it essentially mirrors the data input to the output. To put it simply, the tri-state buffer has a dual role. It either passes the data from the input to the output when enabled, or it steps back and goes into a high impedance state, allowing other devices to control the communication line when disabled. To sum up, the behavior of a tri-state buffer is controlled by its enable input. When enable is set to 0, the buffer is in a high impedance state, irrespective of the data input. When enable is set to 1, the buffer actively transmits data, mirroring the data input to the output. This shows how a tri-state buffer can take on three different states, depending on the inputs. It's a sophisticated yet straightforward logic gate that plays a critical role in digital systems, allowing for efficient and controlled sharing of communication lines. So, next time you're working with digital systems, remember the handy tri-state buffer and its clever behavior. So, where do we use these tri-state buffers? Excellent question. Tri-state buffers are like the unsung heroes of the digital world, quietly working behind the scenes in a number of applications. Firstly, consider bus systems. These are like highways for data, where multiple devices need to share a common communication line. Tri-state buffers play a crucial role here. When a buffer is disabled, it goes into a high impedance state, essentially making itself invisible. This allows other devices to drive the bus, ensuring smooth data traffic flow. Next, let's talk about memory devices, such as random access memory or RAM. Picture a library with several librarians. All of them can access the books, but only one at a time. Tri-state buffers make this possible in the digital realm, allowing multiple memory cells to share a common data bus without causing a data traffic jam. Continuing on, tri-state buffers also come into play in multiplexers and demultiplexers. These devices are like traffic controllers, directing data from many inputs to one output, or vice versa. Tri-state buffers help by selectively enabling or disabling data paths, making sure the right data gets to the right place at the right time. Finally, consider the controlled interconnection of multiple digital devices. It's like a well-organized social gathering where everyone gets a chance to speak without talking over each other. Tri-state buffers ensure that digital devices can share lines without causing contention, promoting harmony in your digital systems. In all these scenarios, tri-state buffers provide a mechanism for efficient and controlled sharing of communication lines. They reduce the likelihood of contention and allow for more flexible interconnections. It's like having a well-trained orchestra conductor, ensuring each instrument plays at the right time to create a harmonious symphony of data. As you can see, tri-state buffers are versatile and used in many areas of digital systems. So the next time you're marveling at the smooth operation of your digital devices, spare a thought for the humble tri-state buffer, working tirelessly behind the scenes to keep your data flowing smoothly. Let's see a tri-state buffer in action now. Imagine a straightforward circuit consisting of an enable input, a data input, and an output. This circuit is a representation of a tri-state buffer. Now let's put this buffer through its paces and see how it behaves based on the enable and data inputs. When the enable input is set to 1, the tri-state buffer comes to life. It's active, it's alert, and it's ready to pass on the data input to the output. The data input could be either a 1 or a 0, but regardless of its value, the tri-state buffer faithfully delivers it to the output. So, in essence, when the enable input is 1, the tri-state buffer is simply a conduit, a faithful messenger that relays the data input to the output. But what happens when the enable input switches to 0? The tri-state buffer takes a step back. It goes into a high impedance state, a state where it's not actively driving the output. It's as if the tri-state buffer says, "All right, I'm stepping back, other devices, you have the floor." This high impedance state allows other devices in the system to take control of the bus, to drive the output without any interference from the tri-state buffer. This simple example circuit, with its enable input, data input, and output, encapsulates the essence of a tri-state buffer. It shows how the buffer can be a faithful relay, delivering the data input to the output when enabled. It also demonstrates how the buffer can step back, going into a high impedance state, allowing other devices to take the reins when it's not enabled. The beauty of a tri-state buffer lies in its versatility. It can actively participate in the flow of data, or it can step back and let other devices take over. It's a master of adaptability, capable of fitting into various scenarios and adding value in each one. This example clearly demonstrates how a tri-state buffer works and its importance in digital logic and design. So, what have we learned today? We've delved into the world of tri-state buffers in digital logic and design. We've discovered that these buffers operate in 3 states: logic high, logic low, and high impedance. This third state, the high impedance or floating, allows multiple outputs to connect to a common bus without causing a short circuit. We've examined the structure of a tri-state buffer, which typically has one data input, one control input, and one output. We've also explored the behavior of tri-state buffers through a truth table, and we've seen how the enable input controls whether the buffer is active or in a high impedance state. We've looked at various applications of tri-state buffers, from bus systems to memory devices, and even multiplexers and demultiplexers. We've also examined an example circuit to see tri-state buffers in action. And that's all for tri-state buffers. Remember, they are key to efficient and controlled sharing of communication lines in digital systems.